Hello, and welcome to take 3 of circuits I can't do. Okay, so we'll be doing RLC circuits, trying to find V of capacitor in terms of T. So because this is a second order, this is going to involve a second order differential equation. Okay, so also take note that all of our sources are step functions, so these don't start until after 0. So at 0 minus, they're not going to have anything. So just from that assumption, we have VC 0 plus, which is equal to VC 0 minus, is going to be 0. And VC prime 0 plus, which is equal to IC 0 plus over C, is also going to be equal to 0. Because the capacitor is going to have 0, because there's no source at it at 0 minus, so IL 0 plus is going to be 0, so what's going to be flowing around is also going to be 0. Okay, so first thing we want to do is source transform this. So we're going to want to make because we want to make the whole entire thing a series circuit, we're going to make this 80. Volts, and we're going to move this up here to 4 ohms. Okay, so now we have that. So we know alpha for a series. Let's do alpha S, just because we know alpha for a series has the equation of R over 2L, which in this case is going to be equal to 4 plus 3 plus 5, which is 12. Over 2 times L, which is 0.25. So that's going to be, what, 6 times 4, so we know this is 24. And the angular whatever W naught is going to be equal to 1 over square root of LC, regardless of the circuit configuration. And from this we can get, this is it. Okay. Okay, so 1 over the square root of 0.125 is going to be equal to 2.8284. So we can just write over here, alpha is equal to 24, W naught is equal to 2.8284. So obviously it's going to be overdamped just because alpha is much larger than W. And we can confirm that by having a real roots when we do S12, which is negative alpha plus or minus the square root of alpha squared minus this W squared, which so happens to be the square root of 8, so this is just 8. And so we can get negative 24 plus or minus 576 minus 8, 23.8. 23 point, yeah. Okay, so when we do that, we find that S1 and 2 are both equal to negative 24 plus that, negative 24 minus that. So we have S1, 2 is equal to negative 47.83 and negative 0.167. Okay, so now we can start to make our differential, and because it's overdamped, we know that the equation for that's just simply equal to e to the negative S1, which is negative 47.83t, plus b e to the negative 0.167t. Okay, and this is when our conditions come into play, which we found out earlier. These are both equal to 0. So VC 0 is equal to, or VC 0 plus is equal to 0. So this is V of t. Yeah, also I forgot to mention, We also have to add the supply voltage, which, because these two are clashing, it's going to be positive 40, negative 40. Yeah. Yeah. Okay. So it should be minus 40 over here. Because when you combine these, this is going to be positive 40 over here. But because the plus side's here, it's going to be negative 40. Okay. So we know that V0 plus is equal to 0 volts, which is equal to, when you plug in 0 for the T's, what you do is the E's become 1s, so you have A plus B minus 40. So we have here that A plus B equals 40. So after that, we can do the same thing with our derivative. Given that the derivative is equal to 0, we know that negative 47.83a is going to be equal to positive 0.167b. So given that ratio, we can calculate that negative 47.83 divided by 0.167, so negative 286.407a is equal to b. Plug that back up into this equation here for b. So just that plus 140 divided by that answer is equal to your a. So we have an a. Just a second. We have an a equal to negative 0.1402, and from that, just multiply that by negative 286.407, and our b is going to be equal to 40.12, or sorry, 40.14. Okay, so now we can write our final equation as v of d is equal to negative 40 plus, or no, minus 0.1402 e to the negative 47.83 t plus 40.14 e to the negative 0.167 t. Yeah, so sorry for the cut in the middle, but this should be it. I'm so bad, I'm messing up so much.